We are starting in a few minutes. I hope you are having a beautiful day so far.
presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you on to today's stream here today for today's lecture. So, before we get into what we're talking about today, which will be the pumping lemma and using it for proving that languages are not regular, I have a couple things I want to make sure to mention. So the first thing is I do have a survey asking about availability of people that watch my content here. So, if you're interested in that, check out my social media links, or depending on where you're watching this, it'll be in the description. So please check that out. I'm just going to put up the chat. So for everybody that's watching, good morning. Depending on where you are, good afternoon, good evening. Hope you're having an amazing day so far. But please, if you got a couple of minutes, just fill out the little survey. It just tells me a little bit more about your availability when it comes to calibrating live programming for us. So, other than that, if you want access to today's notes, which includes the examples I'm going to be going through today, which is primarily what we're going to be doing here today, please consider supporting on patreon.com/pagewizard. They'll be accessible on Patreon. Right, Miss Kitty? Yeah, we ought to make sure to support on Patreon, right? Is that what you're saying? Well, that's awfully nice of you, Miss Kitty. You didn't have to say that. But yes, so the notes for today's live lecture will be available on patreon.com/pagewizard at the supporter access tier and above. Note that there's other ways to support as well, such as Subscribe Star. But of course, if you just want to support this work, just generally, make sure you give a like, comment, follow, subscribe, do your thing, okay? So, of course, tell your friends to come join the fun. I know there's a lot of people learning computer science and they're looking for ways to enhance or boost their learning in computer science. This is one affordable way to do that. In fact, I would argue it's one of the most affordable ways to do that. At least if you're looking for an authoritative source to learn computer science from. It's Page Wizard Games Learning Entertainment. So, for those that have not been here, my name is Dr. Daniel Page, but you can just call me Dan. We always have a good old time here. Right, Miss Kitty? Yeah, exactly, Miss Kitty. But how's everybody doing today? I hope you're having an amazing day. And I just shocked Miss Kitty with a little bit of static electricity there. I don't think she liked that. Miss Kitty, we're going to be talking about the pumping lemma today. Are you excited? Are you excited, my friend? I think she is. I keep shocking her by accident. Yes, we have our dinosaur friend. Yeah, right, Miss Kitty? Yes. Oh, you like this. You like the dinosaur friend. I see. I didn't expect that one. That was on my bingo card for this year. To see if you would actually, for some reason, you appreciate the dinosaur. The little dino. So, I'm going to give you a game plan for today's lecture. Miss Kitty, those are my notes. Those are the notes for today. So, just a couple quick things. So, if you have questions during the lecture, please just put it in the chat. Please participate in the chat. It helps people know that they can come and join the fun. You can talk about whatever in there. Of course, be decent. Don't be too edgy. A little edge is okay, but not too edgy, okay? So, if you have questions, though, please put them in the chat. If you're not sure about something, just ask about it. Or if you're looking for more from me to help you out going through this stuff, please let me know. Or if you just have a general question, I'm happy to hear. So, other than that, if the chat is visible on the screen, the text-to-speech specifically from Twitch will be audible. So, I must stress that when the chat isn't visible on the screen, it will not audibly play during the stream. So, but keep in mind, I can hear it. I have an earpiece in, and also I can see the chat right there. So be aware that I can see the chat. It's a blessing and a curse. So if you want to give me a good joke in there, that's always a good time. So other than that, do consider checking out more of the educational content. And I must stress that we're live typically on Tuesdays and Thursdays. So this is our live lecture. Later this week, we'll have a stream. We're playing Chrono Trigger, which is a good old RPG for the Super Nintendo days. But yeah, so let me give you a rundown for today's lecture. So I gave you kind of the setup. Miss Kitty, I was going to take those, but oh well. Yeah, you can stay here just for a little longer, Miss Kitty, okay? Okay. Just a couple quick things. So what I'm going to be doing is I'm going to recap last time when we talked about the pumping lemma, what it is, and how we used it last time to prove that a language wasn't regular. So recall, a language is regular if there exists a deterministic finite automaton that recognizes that language. So what we have here is one theorem, a property that all regular languages have, that we can actually use and pick up to show that there are languages that are not regular, which we'd previously not really given any treatment to. So what you see in our first example last time, that's what we're going to be covering today, is we're going to be doing lots and lots of examples. So I have at least a few examples of proving languages are not regular. If you want to see more examples, let me know and after this or during the chat if you're curious. If you want to hear some more examples, let me know, or if you want to see more examples in the notes, please let me know. So that's what we're going to be doing today, is we're going to see more examples of proving languages are not regular. We're going to use this pumping lemma, which is true for all regular languages. So just remember, keep in your mind that if a language is regular, then it has to satisfy the pumping lemma. The contrapositive of that statement is that if a language doesn't satisfy the pumping lemma, then it isn't regular, right? So that's one key detail that's very helpful for us. It gives also a recipe to prove that a language isn't regular. It gives you a tool for doing that. So I'll be walking us through this is the pumping lemma. I'll give you a recap of what this is. We proved it previously. And then I'll walk through the strategy if you want to use contradiction, which is what we're going to use, how you'd use the structure of the pumping lemma to derive a contradictory statement, at least the typical game plan. So if there aren't any questions, it's rather quiet here today, but that's okay. It's okay. We'll get into things here. So what we're going to start off with before I get into our examples is I'm going to give us a walkthrough of this, go through a strategy of it. I've talked about this previously last time. Well, not last time, but the time before. Last time we talked about cryptography, but the time before that. Last time we were talking about automata theory. So I showed you something kind of like this before. So I'm hoping to give you more of a game plan technique. So if you're wondering how all of our examples are going to play out, I'm going to lay it out here so that you have a skeleton for where you could start, a good starting place for a contradiction proof. Not everyone will follow the exact same structure, but most certainly this will be a very common way of going about it. Another thing. Once I do this, I'm going to go through some techniques for selecting the string that we use that yields the contradiction. So I'll be talking about that as well, giving some time to this. So before we get to our examples, I'm going to give us some tips for how we can prove a language isn't regular using the pumping lemma. So that's what the game plan is today. I know it took a little longer than expected. Miss Kitty decided she wanted to go a little crazy. See a kitty over there napping. But anyways, well, why don't we get started? Let's get started, everybody. Is everybody excited? I sure am. So let's get started. So previously we had seen an example of proving a language is not regular using the pumping lemma. Now, before we get into seeing some more examples, I thought it'd be a good idea we kind of revisit what we talked about, so that you get a general game plan. So this is a common way of going about using the pumping lemma to prove a language isn't regular via contradiction. So recall this is the pumping lemma. So for any regular language L, there exists this constant called the pumping length, such that when I have this pumping length, and I must stress this depends on the language in question, depends on L. You can't just pick any P. It just exists, right? But it is the case that if you give me any string in the language such as length is at least the pumping length, there exists a way to dissect W into three parts, X, Y, and Z, such that it satisfies the following three properties. So it's really a question about it's about a sufficiently long string. So if the string is long enough, there's going to be a way to be able to decompose or dissect it into three parts such that the Y part, the middle part, isn't empty, but the first part of the first two parts, X and Y, it's going to be at least the pumping length, and it'll be that you can keep producing more and more strings that belong to the language for any k greater than or equal to 0, x, y to the k, z. That means you could repeat the y part 0 or more times. So I got x, y to the k, z. This belongs to the language as well. So you might say, Dan, well, when we see in our example of proving a language isn't regular and we use the pumping lemma, we used contradiction. I thought it'd be a wise idea I go through the general game plan I used in that proof. So if I were going about this using contradiction, what's the first thing I do in a contradiction proof like this? Well, I assume that the language is regular, right? So what I do is I assume L is regular, right? So if my goal is to show that L isn't regular, I'll just presume it is. And if it is, then it has to satisfy the pumping lemma, right? So that means that there's going to exist this pumping length P. So you're just given, you get this for free as a result of that assumption. So you're given P, but you don't know what P is, right? Somebody just gives it to you. I don't know who it is, but the point is that it exists, right? Now, here's the catch. Once you have this P, you know that for any string of a sufficient length, it satisfies all of this, right? So if our end goal is to come up with two strings. One string that I'm going to pick out of these ones, right? Because it has to satisfy this for all strings in the language, right? So I want to be able to pick a string such that W is in the language, but then I also want to show you that I could use this fact to come up with another string that should be in the language because of this property here, the third and last one there. I want to say that this is in the language, but I also want to show you that x, y to the k, z isn't in the language at the same time, giving me a contradiction. So I want to pick W such that I can take advantage of some properties here. The most common strategy is to try to get it so that I pick an appropriate k, such that because the pumping lemma tells me this is in the language, I want to show you that that string also isn't in the language, yielding a contradiction. So let's walk through this carefully now. So if it is that I'm given this, and I don't know what P is, so whatever I'm doing in my argument, I can't just fix what P, I don't get a choice of what P is. P is just given to me, right? But however, it has to be that for all the strings, it has to be of a sufficient length, I get to pick W, right? But it has to satisfy this property over here, right? So I get to pick this if I'm trying to come up with a way to derive such a contradiction, right? Because it has to be satisfied for all strings. So I get control over how I pick W. That's actually what I did in the proof. Now, here's the thing. When I pick this, there exists a way to write it such that it looks like this. So we'll talk more about how we pick W carefully. There's a lot of ways you could pick W depending on what the language is, presuming it is non-regular, right? But Anyways, we're assuming that it is regular. But if it is the case that I pick this W, it has to satisfy, if it satisfies that property, meaning it's long enough, I should be able to decompose it like this, break it into the 3 parts. However, I don't know how it's broken into these 3 parts. So we're given, so you can imagine somebody somebody's saying, hey, look, that there's some way to do this, right? I don't know which way it is, right? I don't know. But if I'm careful about how I pick W, I'm able to actually tell you any way that somebody could have decomposed W. But here's the catch. If I'm able to pick W in a clever enough way such that my argument will work regardless of how somebody decomposes this, I should be able to take advantage of these properties over here, regardless of how it's decomposed. However, if I have to pick W in a very in a somewhat more crafty way that requires me a little bit more work, I may have to use multiple cases. For example, it might be that the first or the second part may consist of different kinds of symbols, or maybe that the first 2 parts, say X and Y, consist of the same symbol. That's what happened in our first example. I'll talk more about that in a moment. But the point I'm getting at is that you want to argue in a way such that you're going to make sure that you aren't making any presumptions about how these 3 parts come about. That's the big thing I'm trying to get at. It's a very common mistake students make, is they just assume that X, Y, and Z, like you know exactly what X, Y, and Z are. Often the mistake is that you get it backwards, is that you're presuming that you know what this is because you presume that you fixed it. But the problem is actually that you're trying to form an argument that tells you what regardless of how you decompose it, what it will look like. If you don't know what it looks like, you're going to have to break it into cases. But for a lot of the examples you commonly see, there's often a very nice way you can, depending on how you pick W, that you can argue regardless of how you decompose the string into the 3 parts, that you get these guys over here, right? And that's what you want. You don't want to make any assumptions about how this is done, unless you pick W in a special way that makes sure that X, Y, and Z have a particular form. And then you have to play with it a little bit more from there. Hope that's very clear. This is a common pitfall for students, is that they just sort of say, hey, look, Dan, hey, look, I know that it could do this. But the thing is, there exists some way to do it. I don't know what it is, just like I don't know what the pumping length actually is, right? I don't know what it is. The point is that if you pick W carefully enough, you should be able to make an easy argument about how X, Y, and Z are organized. So for example, you often will assign frequencies, how many symbols of a particular kind are in W, and then break it into cases. Another thing you might try doing is you might try to pick W in a special way such that you know exactly what's in a certain part of the decomposition or dissection of the string into these 3 substrings, such that you can yield a contradiction, which is often what you would like, is so that you don't have to do a lot of work. Because if you could get away with a nice, elegant argument that is correct, that's much better than having to exhaust 3 to 6 cases at least. Maybe less, maybe more, I'm not quite sure. But the point I'm getting at is that you want to make an argument such that you can't make any assumptions about this. Unless you pick W in a very special way, can you point at this and say, yeah, the decomposition has this property, and I need to observe that property. Now, once you have that, once you pick W, you know that there's some way to write this. You don't know what it looks like. Remember, just think of it like it's in a box, right? I want to be able to say something about what's in the box. So I don't know what X, Y, and Z are. I just know if I pick W, that if I looked in this box, hypothetically speaking, I should be able to tell you that X and Y have a particular thing going on, but I don't know what X and Y actually look like. If I were to if somebody just gave me the way it was done. I hope that's clear. So, if I pick W appropriately, and I have this way of decomposing it, then I get these properties. So these are things I know about how this dissection occurs. So the Y part's non-empty. That Y occurs in the first P symbols along with X. But keep in mind, remember, it's at least, it's our XY. The length of this is going to be at most P, the pumping length. So it means it's going to be occurring some part at the beginning of the string. But you remember, I must stress that this is less than or equals. That means that there's other stuff that could happen with the Z part, right? So you might want to take that into consideration when you're picking out this string, because it could be the case that there's a Z component that could be associated with what you're assuming, and that's something that can happen if you pick W in a particular way. The point I'm getting at is that there might be multiple cases. Another thing, and like I said, the end game is to try to get over here, is that I would like to be able to pick so that X, Y to the KZ isn't in the language. So that's how I'm going to yield the contradiction, because the pumping lemma tells me that this is in the language, but I want to pick K. Remember, since it's for all, I get control of how I could pick K, because it should work for any K, right? So if I could do this, this is a very common strategy for using the pumping lemma to yield the contradiction. So hopefully that is clear to everybody. So I thought I would revisit this idea, and I really want to focus in on this part and how you pick the string W. So we're going to talk about that now. And I'm going to revisit an example that we did earlier, where we considered a language that looked like this. Where we had shown that if your string consists of equal numbers of zeros and ones, then we show that this actually isn't a regular language. And we use a strategy much like this to prove it. So I want to talk a little bit about the two things I really want to emphasize: the selection of this W and how this decomposition exactly works. Because remember, I don't know how the decomposition occurs, but I need to be able to consider all possibilities of how it might occur, right? So I want to talk first about the decomposing aspect, and then I'm going to talk about picking W. So let's talk about this. So decomposing X, Y, and Z. So I'm going to lay this in the context of this simple example that we did, just to help us see that there's other ways that the string could be decomposed and how exactly the selection that we used worked. So in the proof, we had actually selected for string W, in this step, we had picked this one, 0 to the P, 1 to the P. So I want to really think about this carefully and see exactly what's going on here. So by how we selected W in the proof, we obtained a simple way, any split or dissection, any split of X, Y, and Z can happen for an arbitrary P greater or equal to 1. So remember, I don't know how this splitting occurs, the decomposing of string W works. So what I do is I pick W in a way such that I can say things about how the decomposition occurs. So how the split happens. So you'll notice, for example, here, and the reason why I picked this one was because if you look at the way the conditions of the pumping lemma work, X and Y occur within the first P symbols, right? So it means that X and Y happen somewhere in this first part, where there's a bunch of zeros. And what we did was we picked our K value, and for the third condition, we picked it such that we obtained a string which had less zeros than ones, right? So you'll notice that when I picked this string, I did it such that I forced X and Y into one part of the string, as opposed to allowing Y to wiggle around or Z to wiggle around. And I must stress that Z can wiggle around, but the point I'm getting at is that I was able to say something about what happens with X and Y, and namely what happens when I pump Y. I didn't really care as much about what was going on with Z, right? In this example. So let me break this out a little bit more carefully now, because I didn't really say a whole lot about Z. That is, you can imagine I have 0 to the A, 0 to the B, I have 0 to the C, and 1 to the P. So this is what the string would look like, where, so like this will be, it could take any one of these here, where P is going to be equal to A plus B plus C, and the length of XY is equal to A plus B, which is at most the pumping length, and the length of Y, of course, is strictly greater than 1. So when I pick this string W, any way that X, Y, and Z are dissected actually looks like this. Did you already see that? So the point I'm getting at is that when the split occurs, I don't know what A, B, and C are, namely because they have relationships with X, Y, and Z. All I know is that A plus B plus C has to equal P by how I pick the string W. So if you actually go back to the proof that we had seen, there's actually several different values for K. Remember that last step where we yield the contradiction. If you actually look at this carefully, you can actually see that different values of K actually work. Many different values for K work to yield a contradiction. Because remember, the Y part here, the point is that it's the 0 to the B part, right? And if I take control of that, you'll notice that, remember, this altogether equals P. That's why I have equal numbers of zeros and ones, right? So what we did in the proof was we took advantage of the fact that this part right here, the Y part, we knew that this Y part has at least one symbol. So what we did was we played around with pumping that Y part, right? So notice that if I use K is equal to 0, we get exactly what we had before. And this is actually what we had in our proof, was 0 to the A plus C, 1 to the P. And notice that A plus B is strictly less than P, right? And that tells you right away that there's less zeros than there are ones. And that's actually one way you could have explained how we yielded the contradiction. That's an alternative way of writing out what we did. So if you wanted to come up with a much more general way of writing out how X, Y, and Z's form might look like, it would look like something like this. And then we pump the Y part. So in this case, I just did it 0 times. And this is the way we actually did it in the proof that we had seen in for our example. So that works. Notice that I can't use 1, right? Because if I used 1, it would mean that I get this back, right? However, if I go k is equal to 2, that means I'm going to pump y such that I get 0 to the a plus 2b plus c, 1 to the p. Where now, if you look at this carefully, you end up with a plus 2b. That's what we had over here for x, y, right? And then I'm going to pack on the c, which is the zeros component, the zeros related to z. Well, look at this. Well, now that is equal to p plus b. And because b is, in fact, positive, that means that this is strictly bigger than p. So that indeed works, right? So you could have went through the same proof and instead would have considered x. So in this case, you would consider x, y squared, z. That's what you would be doing here for k is equal to 2. So you can try more and more values. You can see quite quickly that, that many values. So I'll let you think about which values would work. So it's not very hard to see, but you know for sure k is equal to 1 you would never do for this. Specifically how we picked our string here. But remember, the big thing I'm getting at, remember, for any way W can be split, we need to show a contradiction occurs. Because I don't know how it's done. Because I just know that it's capable of doing this such that we had the 3 properties, right? But I don't know exactly what x, y, and z actually look like, right? Unless I pin down its form based on w, and then I can make observations based on how I pick w. But the thing is I can't just tell you that x, y, and z have, like they say, there's exactly this many, this many, this many. I don't have control over that. Notice that I'm using variables here to say, okay, well, this x part, okay, there's 0 to the a. So a has something to do with how x is appearing to me. B has something to do with how this splitting occurs, and of course C as well does as well, right? So remember, I don't have control over A, B, and C. However, in the third property, the one where I select K, I actually can control what happens with how many of a certain type of symbol, whatever's in the Y part, occur. So I want to pick W carefully such that I can easily control Y. So that's one element of this. So please remember that you don't have control over, like, at least in the most broadest sense, depending on how you pick W, it changes. You could force it into a particular form. But you has to be able, your argument has to work regardless of how the split can happen. So the technique is to pick W in a way such that you force the split to occur in a particular way that you can point out and say something about what the form of that split would be, so that you can pick out K appropriately. So that's the big thing I really want you to make sure to remember here, is that you can't just say what X, Y, and Z are. You just can't do that because you're not given that information. Just like you're not given the information of what the pumping length is. It's the same thing. The point here, and as I'm going to talk about now, is that you can pick W. So what we do is we take advantage of the fact we can pick W to try to force X, Y, and Z to look a particular way, and we make observations based on that. But remember, when we do that, it has to work regardless of how the split can occur. So here's my other tip. So be careful when picking W. So in our example, over there, when we pick this W here, so we pick W, so at least P symbols consisted of 0. Of zeros. So the reason why we did that is that we didn't have to say anything specifically about how many of each there are. I could just simply say, okay, well, it means Y has only zeros, right? Because it occurs to that first P symbols, right? And that's how we played around with it. But if you want to really be careful about how you write it, you could also have written it out like I had over there on the right. So some choices for W work. And when I say work, I'm meaning to yield a contradiction in an easy to demonstrate way. Or just simply work at all. Others won't. So my big thing, and this is to come back over here, and as I said, try to select W so that the ways W can be divided into X, Y, and Z are easy to determine. Whereas I would say that you're trying to force it to have a particular form so that it's easy for you to say something about the X, Y part. Namely, so I could say something about Y. So that when I pick it, I could guarantee some property occurs. Are easy to determine. So I want to do a couple of examples just to give you some ideas for how you might go about this and how you could pick it. Because there's other ways you could have picked W, but be careful. So one thing I need to be very clear about is that in more complicated examples, you may pick W in a way such that you might need to exhaust more cases. Because like you've seen over here, when I wrote out those zeros and ones, I assigned variables that are associated with how X, Y, and Z are exactly split. How that split occurs. Now, here's the catch. If you pick W, depending on what example you're dealing with, it may be the case that that way those variables would be allocated, their values, depends on the split. And if it's a little bit more complicated, it might be that there exists more than one case for which the split might affect Y. And your form of X, Y to the K, Z. So what I'm saying is, in our cases, it's going to be really nice, but often if you're dealing with a much more nasty example where finding that W, which in many cases you can find, but it might be the case you might need more cases because you might not be able to easily say, depending on what the X, Y, Z split does, depending on what that does, what it will look like. And then you need to be able to exhaust all of the ways that that string could look like depending on X, Y, and Z. Remember, you don't get to have a choice of what X, Y, and Z are. So you have to try all of them. So the whole trick here is that we pick W such that we force it to have a particular form so that I don't need a whole bunch of cases. But you might have to do that, depending on how you pick W. So let's consider some examples. Let's consider if you picked we picked W, where it's 0 to the P over 2, 1 to the p over 2, with ceilings applied to both of these, meaning I'm always going to round up the result to the next integer if it's not an integer. So you might be looking at this and say, okay, Dan, first, is this W work? Is this one that's going to work well enough for us? Well, remember, the first thing that you need to make sure of is that the string W's length is at least the pumping length. So remember, I don't know what P is, but the thing is, it has to be at least P. Well, notice that if it was just P over 2 like this, well, P over 2 plus P over 2 is P, right? Well, remember, it could be the case that depending on what P is, that might end up being a fractional number, and that means that we can't have such a thing as a half symbol, okay? So we're rounding appropriately, but you'll notice that because of that, I'm able to guarantee that this is not going to be rounded down, and this is going to be something that will be one bigger if needed. But the point is that if you pick this, the string is going to be long enough. So it's going to have length that's going to be at least. So the length of this W is at least P, right? Because the ceiling of P over 2 plus the ceiling of P over 2 is at least P over 2 plus P over 2, which is equal to P, right? So yes, it indeed has that property. But there's a more of a catch with this way of picking W. Do you see it? There's a bit of a catch with this one. So we took advantage of the fact that all of Y is sitting over where there's zeros, right? So we can easily make that determination by how we pick W. However, in the catch, if you tried this, and I encourage you to try it, you might need more than one case. That's why I'm getting it. Is Y can consist of, and it could be the case that it could be all zeros. It could be the case that it's zeros and ones. Or 3, only ones. So now what you have to do is now you have to make sure that you check all 3 of these possibilities, right? So in your proof, instead of it having where we just make a simple observation about the form like we did, you would have it where you consider all possible or all 3 ways that the split could occur. And then you'd examine what happens. And then you go through the same strategy we did before. And because you considered all 3 of these possibilities for Y, then it could be, then it has to be the case that you get the result that you're looking for, right? So this example, you shouldn't have issues with this example. However, you'll find very quickly that it's a little bit more work because now you have to look at these carefully. Let's consider another example. So you would yield a contradiction in each one of these cases. That's what actually you would do in this case. So it's like if we did our work but do it 3 times. Now, let's do another example. Let's suppose that you picked this. Something very similar. Suppose that we picked 0 to the P over 2 were the floor, and I have 1 to the P over 2 were the floor. Can I pick this for W? Can I pick this one? Is this going to give me any troubles? Any troubles at all? If I pick that as W? Well, let's go to our checklist. First, we need to make sure that the length it's long enough. Otherwise, we cannot use it. Well, let's take a look. Well, by the similar reasoning, right? We have P over 2, we have P over 2. And then, okay, so if it was P over 2, that's at least P. However, I'm rounding down these. Consider if, say for example, the pumping length just hypothetically was 1. That means it would be 1/2 rounded down, which is 0. And then you have 1/2 rounded down at 0. That's 0, right? It's not 1. Because that's what 1/2 plus 1/2 would be. So in this case, is not guaranteed that W is at least P. And what circumstance is it, though? When would we be able to just ignore the floor signs there, where we apply the floor? Well, it divides it by 2, so anytime it's even, right? Whenever, except when P is even. If P was even, you're okay. However, like I said, you have no control over what P is. So I would not recommend you pick that first W. It won't be long enough. It's not going to cut it. So those are some tips I'm going to give you for proceeding with proofs for applying the pumping lemma to show a language is not regular. So remember the 2 big things. First, you have no control how the split occurs. The big tip that I'm going to give you is you pick W carefully so that you can make sure that the split, if it happens, it has a particular form that's easy to determine. So you want to think of it like you're forcing the string to have a particular form. However, remember, you don't know how X, Y, and Z are organized. You want to try to force W in a way so that X, Y, and Z have a particular property to them. So like in my example here where I pick 0 to the P, 1 to the P for this language and that proof, we did it so that I can force it so that X and Y always are zeros. Z might consist of some zeros and the rest of these ones, but the point is that Y is always going to consist of zeros. And that's what we took advantage of and we explained carefully over here on this side. So please keep that in mind. The biggest mistake, biggest pitfall students fall into is they don't understand that you don't have control over X, Y, and Z. You don't get to pick them. Our argument has to yield a contradiction regardless of how the split occurs. But yeah, so those are some of my tips. Those are some of my tips. So, are there any questions about the pumping lemma before we get into our examples now? So I thought I would rip this open and go carefully into things. That's what the purpose of this was. Is that you can see how we go through the reasoning. I gave you some tips about how you would go about it and some tips for how you'd try to think about these decompositions or splits and how they relate to picking W. Usually, as we're going to see in our examples, when you pick W, you could try to take advantage of the fact that it has the form based on what W looks like. And then you say, hey, look, I've picked W in a way such that first it's in the language. Remember, it has to be in the language. If it isn't in the language, you can't pick W. But the point I'm getting at is that you have to be careful about how you pick W. If you pick W carefully, it makes everything else flow nicely, so you don't have to have a whole bunch of cases like this. May be avoided in a lot of cases. As we're going to see in all of the examples we're going to have here, I'm pretty sure I can handle all of them by just simply picking W carefully. I can't claim to you that it works always, but most certainly is a good place to start. My apologies. So if you have any questions or if you're checking this out, let me know how you're doing. So I'm just going to erase the boards here, and we're going to get into our examples. Just going to grab some water here in a moment. Just got to finish erasing. we're going to be seeing a trickier example first. I thought it would be a good way of warming us up, just to make sure we really understand what we're doing here. So I'm going to start off with a trickier example, and then we'll get into some more cozy examples. Just to make sure that we're really convinced we understand how the pumping lemma works. Because if you don't understand how the pumping lemma works, this is going to be rather tricky to apply it in the form of a contradiction proof to show that a language isn't regular. Okay, so let me just erase a few other things here. So let me just write the example on the board, then we'll get started here. So we're going to consider L prime, or LPR. So it's going to consist of only ones. It's going to be a unary string. That's what we're going to be proving next. We're going to consider all unary strings such that if you actually examine the length of the string, or the number of ones, it's a prime number. So next we're going to be considering the next, well, sorry, I'm getting really excited here. So next we're going to consider this language, and we're going to try to prove that it is not regular. So what is it? It's going to consist of all unary strings such that if you examine the number of ones in the string, it is a prime number. Or just simply we're examining the length of the string W, and we're asking, is the length a prime number? So for those that need a reminder, this is actually going to play an important role in this proof, is that if I look at the divisors of a prime number, how many divisors does it have? Well, it's exactly going to be equal to 2, right? So it has to be that these two divisors are 1. And so if I talk about the prime number q, then it's 1 and q. Those are the only two divisors it's allowed to have. That means that if I give you a number and it consists of something that isn't 1 or q is a prime number, it's most certainly going to be a composite number. Sorry, I'm getting really excited here. So what we're going to be trying to do is we're going to try to take advantage of the fact that prime numbers only have two divisors, namely the prime number and 1. So if I could show you that that I could guarantee you that one of these isn't 1, then we're okay, right? So let's proceed. So how do we start typically if you want to use a contradiction proof to show that a language isn't regular? Well, one way we could go about this is using the pumping lemma, right? So I'm going to start off by assume that LPR is regular for the sake of a contradiction. So then I get the pumping lemma, right? Then by the pumping lemma, what do I get for free? I get the pumping length, right? I don't know what the pumping length is, right? It's like if I had a conversation with my dino friend about the pumping lemma, my dino friend would tell me what P is, right? But I don't get a choice of what P is. My dino friend does, though. Because dino friend knows something about the language that I don't know yet. So then, by the pumping lemma, there is a constant P satisfying the conditions of the pumping lemma. So I'm just going to abbreviate pumping lemma as PL, just to make this a little easier for us. Now, here's the great part. Here's another thing that we know about prime numbers. There's an infinite number of them. So I can always know that there exists one so that I can do something like this. Consider some prime. I'm going to call it M. It's going to be at least the pumping length plus 2. You might ask, why is the plus 2 there? It's going to be helpful for us later. So M exists as there are infinitely many primes. So if I give you like P plus 2, I most certainly could find you a prime number that's going to be at least P plus 2. So what we're going to do is we're going to pick W. So remember, I have control over W because if I pick a one that is in the language and length is at least the pumping length, we're okay, right? I get control over that because it should work for any string W that has this property. If the pumping lemma holds, right? So let's go. So I'm going to let W be equal to 1 to the M. Now remember that M is what? It's a prime number. So 1 to the prime number, that's indeed going to be in this language because it's the number of ones, right? Then since by our selection of W, it's at least the pumping length, what do we get? There is a way to divide W into the three parts X, Y, and Z so that the Y part isn't empty, right? So that the Y part isn't empty, isn't the empty string, and the length of XY is at least P. The pumping length. Now, for simplicity, I'm going to throw around some more notation here, so just follow me very carefully with this. For simplicity, that says simplicity, by the way. The M has just decided to be a little more excited than it usually should be. Simplicity. For simplicity, we're going to let the length of Y be equal to D. And whatever I'm left with for XZ, so if I consider the first and the last part, this is going to be equal to M minus D, right? For my selection here, that makes sense, right? Because this would be, so I'm saying that I'm going to call this D here. So everything else has to be M minus D, correct? So now, here's what we're going to do. We're going to consider another string that should be in language LPR. So consider X, Y to the M minus D, Z. Well, let's think about this carefully. First, let's think about this. We know M m is at least p plus 2. So that's going to definitely be it's going to be something, right? But here's another thing. We know that d here, d most certainly can't be more than p, right? Likewise, d is in fact the length of the y part, right? Of w. So we know that this will end up being some non-negative value. I don't know what it is. Remember, I don't have control over that. I just know that this is divided into these three parts. However, that string, most certainly because of that, is in the language. Which is in LPR by the pumping lemma, right? That's what the pumping lemma tells me. Well, what can we say from here? Well, let's think about this. Let's write out what the length of this string is. Let's take a look at what it does. I want to know what's happening here. Well, the length of xy to the m minus d, z, this is going to be equal to, of course, there's the xz part, right? There's just x and z. And then there's going to be whatever's here, right? Well, we know that the length of the y part, this y part right here, that's d, right? But it's done m minus d many times, right? So it's m minus d times d. Well, let's rewrite out what this is. Well, what's the length of xz? What's the length of xz? Well, it's m minus d, right? So we're going to put that in there. And notice I have m minus d plus m minus d times d. So how many m minus d's do I get as a result then? Well, there's d plus 1 many of them then. There's d plus 1 many m minus d's. Which has two factors, right? If you look at it, I've factored it. I deliberately wrote it like this so it looks like it's two factors, right? Two factors. D plus 1 and m minus d, right? Well, this comes back to our lovely friend over here. Is this going to end up being... Remember, the way the language is defined is based on the length of the string, right? It's number of ones, but it's a unary string. So if I'm able to tell you that this isn't a prime number as a result, it most certainly isn't in the language, right? And we get our contradiction. So I needed some way to argue that that is indeed the case. So let's now look at those two factors there. Then let's look at the two factors now. So let's examine each one separately, and we're going to use the properties we know about those two factors to say something about whatever this length of the string has to be. So let's take a look at this. Then d plus 1 is greater than 1. Why can I say that? Remember what d is. D is the length of the y part. As y isn't empty, right? So that means that d is at least 1. So that means if I take and add 1 to that, then it has to most certainly be bigger than 1. And m minus d is bigger than 1, as m is at least p plus 2, right? That's how we picked m. There's some prime that's at least p plus 2. And since we know, of course, because the length of the xy part is at most p, that most certainly means that d is at most p. Get very excited here. that means that D is going to be equal to the length of Y. That's what it's defined as, which this has to be at least this, which is at least that, right? By the pumping lemma's conditions. But what does that mean? Well, what does that mean then? Well, let's think about it. Well, I have this inequality, right? And it says, well, let's see what's happening here. Well, we know this right here. So if I were to put P over there, it'd be M minus P is greater or equal to 2, right? But notice that D is in fact going to end up being at most P, meaning I could easily just put D in there and it still will satisfy the inequality, right? Right? I'm just taking a number, I'm subtracting something that's a little less than it. Resulting in M minus D is at least 2, which of course this is strictly bigger than 1, right? Now, let's look at our two factors here, and let's think about if this was a prime number. So remember, I told you that has two divisors. So if I'm able to multiply two numbers, it has to be that whatever I get here has to look like a 1 and a prime number. In this case, it would probably be, it has to be some prime number, right? Well, let's look. But you'll notice very carefully that I have these two factors in a very nice way, so that when I look at the length of x, y to the m minus d, z, this is going to be equal to d plus 1 times m minus d. We've argued that this is strictly bigger than 1. So that's not the 1 that I have here, right? This over here is also bigger than 1. So if I take two numbers that are strictly bigger than 1, can it be a prime number then? Can that be a prime number? No, right? It can't be a prime number. There's no way this could be a prime number. It's a composite number. So both factors are at least they're strictly bigger than 1. I was getting a little excited there. Are strictly greater than 1, implying x, y to the m minus d, z is not prime. And what does that mean? It's not in LPR, which is a contradiction. Completing our proof. Therefore, LPR is not regular. But yeah, so there's an example there. It's pretty neat. It's a little trickier one, but if you walk carefully through it and remember what a prime number is, it's a piece of cake. Once you've got all those building blocks in place. So any questions at all about this example before we proceed? So I thought I would start off with a trickier example first, and then we'll start getting into some, what I would consider some softer examples. They're still a little tricky because they're not going to be exactly the same as our first example, because the whole idea here is that I try to take it so that I picked the prime carefully enough so it was big enough so that when I take and look at whatever happens when I subtract off parts of it, I end up with something that cannot be a prime number. My apologies. I'm trying to take advantage of the way that we've formulated out the string. Remember, I don't know what x, y, and z are, but the thing is, no matter how x, y, and z are dissected into those substrings, it doesn't matter. Notice the argument still works. So let me just erase the board. We're going to get to our next example. I thought we would explore palindromes. You may have heard of these before. For example, if you've heard of a word that reads the same forwards and backwards, you've heard exactly what I'm talking about. So, for example, race car. If you read race car forwards from left to right or right to left, it's still race car. We're going to consider binary strings that look like that. I'm just having a fun time erasing the board. This eraser's giving me difficulties at the moment. Miss Kitty? What you doing? What? What little Miss Kitty? What you doing, Miss Kitty? Are you behaving yourself? Just gonna erase the boards. Then we're gonna get to our next example. We're gonna talk about palindromes. But if you have any questions, just put them in the chat, okay? Also, tell me about your day. Hopefully you're having a wonderful day. Miss Kitty, what do you want? I don't know what you want, Miss Kitty. Miss Kitty's a little excited. Just gonna write a few things up here before we get started. So let's get into our next example. Miss Kitty, why don't you go over there for a bit? Yes, go over there for a little bit. No. Go over there for a little bit. You're being funny. Yes, hello, Miss Kitty. Miss Kitty, can you go over there, please? Miss Kitty's getting a little excited, okay, everybody? Well, okay, fine. You can stay here as long as you behave yourself, okay? Okay, Miss Kitty? Hey, you're a funny kitty, I know. But anyways, let's get into our next example. Miss Kitty, don't you start attacking me. You're so funny. Yeah, you're so funny. Yeah, you're so funny. So previously we've considered examples for where a language isn't regular. Now, I thought I would consider a family of languages, so I'll tackle one of them and then I'll show you how you'd proceed with another example. So we're going to consider the language of palindromic strings. So these palindromes, if you've never heard of these before, they're simply strings that are read the same front to back as they are back to front. You may have heard of the word like race car. Race car is a palindrome. Because if you take the word race car, read it left to right, it says race car. If you read it from right to left, it's race car. So this is an example of a palindrome. So here's another example, 101101. So notice this is an odd length one, because you'll notice that the length of the string is odd. And a typical thing you'll run into with these odd length palindromes is when you read it, you'll always get this middle one here that sort of just comes up for free. There's a symmetry that happens across the middle, but we get a free one in the middle. So we're going to be considering these odd length palindromes first. So this language isn't regular. So we're going to consider El Palo, which is going to simply be all strings consisting of of A's and B's. I thought I would change it up a little bit. A's and B's, where W is an odd length palindrome. We're going to show that this isn't regular. El Palo isn't regular. So what's the first thing that we do when we want to try using the pumping lemma in a contradiction proof? Well, first, if we want to use contradiction, if we want to show that it's not regular, we're going to assume that it is regular in order to derive a contradiction. So we're going to assume El Palo is regular. So if I want to use the pumping lemma, which I'll just abbreviate as PL, what happens? Well, I end up getting this constant P, which we call the pumping length. I get that for free when I assume this. So it follows from the pumping lemma that there is a constant P that follows its conditions. So now we got to pick the string. Now, we're going to be very careful here because remember, we need to make sure the string's in the language, right? Has to be in the language. That's one thing. It has to be at least the pumping length and its length. But I want to pick it such that it makes it easy for me to determine the form of the string, regardless of how the pumping lemma dissects the string into three substrings, X, Y, and Z. So a tip I was going to mention here is that I end up with this, I sort of have a symmetry that happens here where I have a free spot in the middle. That's what happens with these odd length palindromes. So why don't I try to do something with that? So I'm going to let W be A to the P, B, A to the P. you'd agree with me that this is indeed a palindrome, right? It's just going to be a bunch of A's, but there's going to be exactly P of them, then a B, then there's going to be exactly PA's that follow the B. Similar to the form we have here, except now I literally just made them all A's, right? I have a bunch of A's, but there's exactly P of them. Then I have a B, then I have a bunch of A's, but there's exactly P of them, right? So this is indeed an odd length palindrome. So that's indeed in the language. As the length of W is at least the pumping length, we can, actually I'll say, as the length of W is at least the pumping length, W can be divided as W is equal to X, Y, Z into the three parts, where the Y part isn't empty, it isn't an empty string, and the length of XY is at least the pumping length. So let's take a look carefully at how I pick W here. So what will happen with XY? Well, it's going to be at most P. I should be a bit more precise, sorry. It's going to be at most P. So what's Y going to consist of? It's going to occur the first P symbols, this Y part. It's going to just be A's, right? So let's look at that. So notice that XY consists entirely of A's. So what I'm going to do is I'm going to let X, the length of X, be I. Because I always like to show you a little bit of a different way to write this stuff out. I'm going to adopt something slightly different so that you could see how I could write out the form of the string. So remember, I don't know what the length of X is. I don't know what the length of Y is. So I'm just going to give them names. Then W will look like this. It'll be A to the I, A to the J, A to the P minus I plus J, because this is everything else. Remember, it's A to the P, B, A to the P. So this would be everything else for my A's. And then I have B, and then I have A to the P. That's what the string will look like. Remember, I don't have control over what I and J are. But that's what it's going to look like. So we're going to consider string X, Y to the 0, Z. So I'm going to pick K as 0, which is equal to XZ. Which is in, of course, El Palo by the pumping lemma. That's what I get out of the last property, the last thing that we get out of that split that occurs. So now, let's take a look at what happens to XZ. However, as Y isn't empty, it isn't the empty string, J has a particular value. It has to have a particular value, right? It's at least 1. And I wanted to make sure that form was over there because so we could use it. And now what I'm going to do is, because now I know that J is at least 1, what I'm going to do now is I'm just going to write out what this looks, what does XZ look like when I take that form and I just pull out what that J component is. So, and xz is equal to 0 to the I, 0 to the p minus I plus j, b a to the p, where we have I plus, so how many zeros are there? Sorry, not zeros. How many A's? For some reason I wrote A's. Sorry, zeros. There we go. We got our A's here. My apologies. They're easy enough to make into A's. So I got a to the I, a to the p minus I plus j together. The I plus j's together. Where, let's look at how many A's I have on this first part here. Remember, this has to equal p for this to be still in the language, right? So I got I plus p minus I plus j. Well, this, notice I have an I there. I'm going to subtract off I here. Well, this is equal to p minus j. But remember, j is at least 1. So that means that this is strictly less than p. So there are less A's in the first part. Than in the second part. Because this is how many are in the second part, right? So what does that imply? Implying xz isn't in El Palo, which is a contradiction, right? Therefore, El Palo is not regular. That's the end of the proof. So we've seen other examples akin to where we pick W and then we make an observation about it. Sometimes we want to get a little bit more precise about what's happening in each part. This helps me talk about the first part versus the second part. So we had our first part, then we have the second part. I showed you that there's less A's than there are A's in the second part. So I have my first part, second part. Now there's less A's in the first part. So you might ask, Dan, what about if I considered palindromes with even length? So that would be, for example, if I had a palindrome that looks like this. So notice that if I read it this way, it has, first it's an even length. So I have 8 symbols here. It's the same as me reading it this way, right? 1, 1, 0, 1, 1, 0, 1, 1. So this is an even length palindrome. How about those? Are those regular? No. You could show that also that the language of even length palindromes is not regular. You might ask, Dan, how would I go about that? I'll give you a tip. It's not really that much of a change, but we need to make sure we keep in mind, and we come back to something that we've seen in one of our first examples. What we want to do is take something out of, like, we compare 2 parts and they have equal numbers. Well, fortunate for us, reading it from forward to backwards versus backwards to forwards, if I tweak with something in the first part, there isn't a free space at all, like we had in this odd case. So if I just tweak with something in the first part, the first half, then most certainly it will cause some problems if I pick the string appropriately. So if you're wondering how I might go about that, you might try the following string for W. So I encourage you to try this yourself. So you might try using this string. So I encourage you to try using this string and seeing if you can make it work. For proving that the language of even length palindromes is in fact not regular as well. So are there any questions? Any questions about palindromes? Any questions at all? Don't be shy. This is a very common exercise if you ever are interested in formal language theory. If you're a computer science student, you're interested in theory of computation and all that stuff, you will run into this topic eventually. So it's something helpful to consider looking into. So that's why we're talking about this today. Because this is a very commonly students encounter this and they tend to have difficulties. Just mainly because of all those quantifiers. Then I also want to show you some examples of how you would pick W and how the decomposition of the string works. So while we're at it, I'll just think about this for a moment. So if you're looking at the B part, you'll notice that there has to be exactly 2 P, many B's over there. You'll notice that if I take away 1, there has to be an odd number on one side. So I mean, that's actually how you get the contradiction over here. You'll notice that I reduced the number here because it'll be 2P, which is an even number, right? So that means that this will become an odd number right here. So you know that the number of B's will suddenly become less, but it'll be an odd number, which means that one side will get a B that the other side won't have. So that's a tip of how you'd go about proving that. So let me just erase the board here. If you have any questions, let me know. Also, let me know how you're doing with your day. I want to know about this. It's rather quiet today. Hope you're having an amazing day so far. So just as a reminder, if you want the notes from today's lecture with all of the examples that we're doing here, they'll be available later today on Patreon at patreon.com/pagewizard. So if you're looking to master proven
So far is good.
languages are not regular.
Bad guess. How's your day so far?
Yeah, it's a little quiet, but that's good. It's fine. It's better than it being chaotic. But then chaos can be a lot of fun too on a stream. We got a couple more examples we're going to go through here. So I thought... Oh yeah, Miss Kitty, she was going a little bonkers down here. Yeah, she's wanted to make sure she said hi a good few number of times.
She is chaos on 4 legs.
That's a funny kitty. So right now, we were just exploring palindromes. So now, let's tackle something. I would argue it's a trickier example than the one we just seen. Maybe not as tricky as the first example we really played around with, but it's something a little trickier. But as long as you understand the ideas that we have here, it's not too scary. Nothing scary about it. Just remember, the trick is to pick an appropriate string, and it makes things much easier. So, there aren't any questions other than lovely ones we got here. But let's get to our next example, okay, everybody? So next we're going to be considering the following language. So let's consider, we're going to call it LS. So LS is going to be the language for which we consider binary strings that have this form. 0 to the I, 1 to the J, such that, I'll make this a 1 just to make that a little easier to parse, where the number of zeros is greater than the number of ones. Or simply, I is strictly bigger than J. So we're going to be proving, that LS is not regular. So we're going to use contradiction to do this. So the first thing we have to do is make sure we clear what we're doing. So if I want to show that it is not regular using contradiction, I have to assume that it is, right? That it is regular. So assume L less is regular. So let's assume that. So what's a property that all regular languages have? The pumping lemma, right? So why don't we use that to help us go about this? Remember, the pumping lemma gives us the pumping length. It is a constant that we can play around with, but I don't know what it is. Remember, just like the conversation I had with my dinosaur friend here. If I say, hey, look, my language is regular, the dinosaur is going to give me P. I don't know what P is until I get it. So my argument has to work regardless of what P is. So then from the pumping lemma, let's say by the pumping lemma, let's go from, then from the pumping lemma, I'm going to abbreviate that as just PL. There is a constant P, that satisfies its conditions, namely the ones for the pumping lemma. That satisfies its conditions. So just as a tip, if you're not sure what I mean by its conditions, I'm referring to the conditions of the pumping lemma. Satisfies its conditions. So the big thing that we have to do is select that string W. Remember, it has to be in the language, has to be an LS, and has to have length at least the pumping length, P. So we got to think carefully about how we pick this string. Now, often in problems like this, where you want to make sure that the number of zeros is greater than the number of ones, it's usually a good idea to try to make one that looks kind of like that, but make it so that you could fudge around with it in a way that you know what's going to happen with the part that you can pump. So here's a suggestion for how I would go about this. So I'm going to try selecting W to be 0 to the P plus 1, 1 to the P. Notice that the length is indeed at least P, but also notice that by putting at least P of the symbols in the zeros part, akin to one of our previous examples, I can guarantee what? So if I look at any way I split the string, so if I have a whole bunch of zeros, then I have a bunch of ones, I know that there's P plus 1 many of these, and there's P many of those. The pumping lemma says that at least there's going to be something going on over here. So remember that no matter how it splits the X, Y, and Z parts, this part here, the X's and Y's, the length of that is at most the pumping length. So if I make it P plus 1, I could guarantee you that Y is going to be some number of zeros. So it's going to consist of 1 or more zeros. So that's why I've selected W the way I did. It makes it easier for me to know what's happening in the first chunk of the first two parts of how, no matter how it gets split, how it's going to work out. Then, and since the length of W is at least the pumping length, W can be divided so that W is equal to X, Y, Z, where the X, Y part's length is at most the pumping length, and Y isn't empty. So now let's use the observation that we have up here. As the length of XY is at most the pumping length, what could I say? Y consists only of zeros, right? It's only zeros. So I'm going to, just because I did this once before, I also want to show you that we could more precisely lay out what the string would look like. So I could compare how many of a certain type of symbol there are. I'm going to go about it this way, but you could abbreviate this a little bit more carefully. And I'm just going to do it this way deliberately. So I'm going to let the length of y, the y part, remember I have no control of what that is, other than I know that it only consists of zeros by how I pick w. I'm going to call this L. So now we're going to consider a string that should be in the language ls. But we're going to have some fun with it. Consider string x, y to the 0, z. So remember, notice that every time I'm identifying a given string, and I'm making sure to be very clear that that is in the language by the pumping lemma, because that's one of the things we get from the pumping lemma, which is in ls by the pumping lemma. Then, now let's play around with what's going on with xz, because that's what this is. That's just xz. Then xz is equal to 0 to the p plus 1 minus L, right? Because I took away L of those symbols. Then I have 1 to the p. And since the length of y is at least 1, or L is at least 1, that means that when I compare the zeros and ones, how many there are, first, p plus 1 minus L is at least, sorry, not at least, it's at most p, right? It has to be at most p. So notice when I subtract off L, because L is the length of y, this is at least 1. It means when I subtract off it from p plus 1, it can be no more than p itself. But what does that mean then? What does that mean then? So, xz does not have more zeros than ones. So xz can't be in language ls, right? Which is a contradiction. Therefore, ls is not regular. So that one's not too bad, right? But notice that the whole trickery that we had here is that we took advantage of the fact that that y part has at least one symbol in it. But we wanted to make sure we picked one in the language. But I wanted to make sure that when it cuts off a symbol, it's done in the 0 part, that it has to be a 0. So that when I cut off at least one 0, that means that there has to be, it's either going to match the number of ones or there's going to be more ones than there are zeros. Pretty nifty, right? So are there any questions about that example there? Any questions about how we proceeded here? Or was it pretty clear? So this one should actually remind you a little bit of the first example we did, where we talked about picking the string. Okay, good. So the whole trick here was that instead of it being that I could guarantee you that there's less zeros than ones, and like in our first example we ever did, here, the whole idea is I want to make sure I could snip off one of these zeros at least. If I could do that, and based on how I picked it, then I could make sure that there's going to either match the number of ones or it's going to be that there's more ones. And since I don't have control of how it decomposes x, y, and z, it might be that it takes more zeros off than just one. It might take several off. So let me just erase this, and we're going to get to our last example, which is also going to introduce an interesting, more hypothetical question. That's going to be a little counterintuitive at first, based on some of the discussion that we've had. I'm going to just lead this in with some discussion here before we get into our example. So listen to me very carefully on this one, which is going to be a little bit weird. So when I talked about languages, and I told you that a language isn't regular, that means that there doesn't exist a deterministic finite automaton for that language, right? Nor does there exist a regular expression or any of these NFAs. None of those exist that can be used to describe that language. Now, we talked about this idea. Now, it gets a little bit weird because at first you think, before we get to our example, I want to dive into this a little bit because I think it's an interesting question. Okay, if I give you a language L, and I tell you, and so suppose that this is language L right here. And I told you that it's actually a part of another language. Call it L prime. So all my strings for L are in here. There might be other strings over here in L prime. So remember, these represent my languages, right? So suppose I told you that this is not regular. Is there anything we could say about L prime? This is going to feel a little strange of a question, but at first you'll have a gut reaction to say an answer on this one. Based on how I drew this, what would you say about L prime? Is this regular or is this not regular? I asked this question for very good reasons.
Not regular.
You'd think that from the way I drew this picture. But this is where it gets a little bit funky, okay? So we're going to see in our next part that actually you can't actually conclude that from this. So it's going to get a little bit weird because there has to be a little bit of a stronger condition for me to allow me to say that L prime is also not regular. So as we see actually in one of our other examples, we talked about the palindromes, right? So palindromes have a very specific structure to them. We talk about the odd length ones and the even length ones. You can show that each one of those isn't regular so that the language of palindromatic strings, this one has to be not regular because that's the union of both of those languages, right? So you can conclude in that case that yes, the whole thing isn't regular because every one of the strings belongs to a language that isn't regular. Now, we're going to see actually in our next example, I'm going to talk a little bit more about this. About how just because one language is a subset of another one doesn't necessarily mean that that language has the same properties. Which at first sounds very counterintuitive because you'd assume, hey, those strings belong to this thing here, so most certainly whatever DFA I give you or regular expression I give you has to describe those too, right? We're going to need to be a bit careful about that because, as we're going to see, just because a string is contained within another language doesn't mean it's as easy to recognize said language. It might be because of it being as narrowly described that it is difficult to come up with a DFA. So let's talk more about this with our final example. I promise I'll give you an example that's going to it's going to be very counter to the intuition of thinking about it like this. And it's a very common mistake students make on exams. That's why I'm bringing it up. Oh, my little turtle friend. I got to pick up my little turtle friend. The little turtle friend, I blew up my little turtle friend's mind. I'm a monster. That's a mind-blowing experience there, my little turtle friend. I'm so sorry. I'm so sorry, my little turtle friend. It's okay. So, anyways, why don't we get to our last example for today? So, in one of our first examples, we had shown that the language that consists of only zeros and ones or A's and B's, whatever it might be, any one string for which the string has equal numbers of symbols one after the other, meaning that there's equal numbers of A's and then an equal number of B's. Like you can't, any language like that isn't regular, right? Well, I want to show you an example of a language for which those strings are contained within another language that is a broader one. And then ultimately I want to answer a question that is a property at least you think of when you think about two sets, or two languages. So imagine I give you two languages like L1, L2, and I claim that L1 is a subset of L2. The question is, can you guarantee that if L1 is not regular, that L2 is not regular. Does that property hold? And we're going to address that here. So, to have some discussion about this, let's talk about a language called L-sum. Just going to get some water. My throat's a little dry. My apologies. Hopefully that didn't sound too gross. So we're going to consider the language L-sum, which is going to consist of 0 to the k, 1 to the l, 2 to the m, 3 to the n, such that k, l, m, and n are all at least 0, but k plus m is equal to l plus n. So you might be staring at this and saying, yeah, what the heck is this? This looks a little bit more complicated than some of the other examples we've seen. Now, don't let the fact that it looks really complicated compared to some of our other examples throw you off. So let's look carefully at the properties it has. So it says that all of these frequencies of how many times one of these symbols, 0, 1, 2, or 3, there has to be at least 0 or more of each one. But it says that the number of zeros and the number of 2's has to be equal to the number of 1's plus the number of 3's. So if you're staring at this for a moment, I'll let you think about it. But it's talking about how many symbols there are of particular kinds. But if you look carefully at this, you're actually going to see another language is actually hiding in here. So, namely, one that we've actually seen before that looks sort of like this. One that looks like that, where we have equal numbers of zeros and ones, for example. If you can see that in here, it's actually surprisingly easy to prove that this isn't regular, using our approach to what we have. So, I want you to think carefully about how you get that out of this. So let's think about it. But let's just dive right in, okay? So let's dive right in. We're going to prove that this is not regular. Oh no, my little turtle friend fell. Gotta be careful. Careful, my little friend. Careful, little friend. Hey, you stay there, okay? You stay there, my little friend. Okay. So we're going to consider L-sum here. We're going to show that L-sum is not regular. So we're going to use contradiction as per usual in our lecture. So we're going to first assume that L-sum is regular so that we could derive a contradiction. So what does that mean? Well, now every regular language, so assume L-sum is regular. So it means that it satisfies the pumping lemma. It follows from the pumping lemma that there is a constant P that satisfies the conditions of the pumping lemma, which I'll abbreviate as PL at this stage. Now, you might be staring at this and saying, Dan, well, how am I going to deal with this condition here? So I need to pick a string that's in this language. Now, do notice how the sums work. So notice that it's k plus m is equal to l plus n. So if you notice very carefully, I can allow two of the symbols to take on no value, one from each of the groupings of these, and then I end up just getting where one of the number of symbols has to equal another number of symbols. So watch this carefully. This is how I'm actually going to pick the string, and this should remind you a lot of how I picked the string in this case. So I'm going to choose W to be 0 to the P, 1 to the P. It just looks just exactly like the one I picked before. Which has length at least P. Now you might ask, Dan, why is that the case? Why is it at L sum? So when you get a little bit more complicated like this, a good idea to explain why. Such a W belongs to L sum. L sum as K is equal to P. So if you look at our constants here, so notice that, so I have K, so notice I'm using P here for the number of zeros. So that's K. K is equal to P. L is going to be equal to P. How about M and N? What are M and N going to be equal to? Can somebody tell me? What's M and N going to be equal to if I pick this string? Notice that there's no 2s, no 3s. So that means that what is M and N? What are they? They don't appear at all, right? So it's 0. So there's just 0. So M is equal to 0, N is equal to 0. And indeed, if you look at this condition here, and indeed, K plus M is equal to L plus N, right? Because M and N are 0. That means that actually all we're doing is we're checking if the number of zeros is equal to the number of ones. And if you actually look at this carefully, that's actually, those are strings that are in that language, right? But that's a whole other aside. That's because of the way we've selected the string, right? Now, by the pumping lemma, W can be divided into 3 parts, right? Into 3 parts, W is equal to X, Y, Z, where the length of XY is at most P, and of course the Y part is not empty, right? And Y is not the empty string. Now, you're going to notice I'm going to use the exact same reasoning I used when I proved that this language isn't regular. Pretty fascinating stuff, right? Because what happens? Well, if I pick my string carefully, I'm going to use K is equal to 0. So I'm going to make it so it repeats the Y part no times. Consider then string X, Y to the 0, Z, which is in L sum by the pumping lemma, right? That's what the pumping lemma says. That's what it... But what can we say about X, Y to the 0, Z? What can we say? Well, let's think about it. Well, if I take away the Y part, well, what's going on with the Y part? Well, what happens? Well, notice what? Notice that XY consists only of zeros. That should sound awfully familiar. So now that we were going to consider this string, well, xy to the 0z is equal to xz. And of course, that y part isn't empty, right? So it means it has at least one symbol. What does that mean? That implies what? So if I look at my sum of how many symbols appear, well, it means that k plus m, remember k is the number of zeros, is strictly less than the number of ones, right? As a result, I get this. But that means it's not a part of the language, right? That means that xz is not an L sum, which is a contradiction. And that completes the proof. So notice that even though that language looked a little bit more complicated than some of our previous examples, inside of it, you can actually see that the strings that I was able to expose as those for which the language wasn't regular, such as in this language, I was able to use those same exact ones in this case. Now, you might say, Dan, is this like a universal property then? So if I have L1 and L2, and L1 is a subset of L2, is it that if L1 is not regular, that L2 is not regular? Well, let's think about it. So we're going to have to be careful. So here's a question. So if L1 is not regular, and L1 is a subset of L2, is L2 not regular? And unfortunately, the answer is that it depends. So in general, the answer is actually no. Now you might ask, Dan, why is the answer no? Why is the answer no if somebody gave me two arbitrary, like if I ask this general question, why is the answer no? And this is the common question, because you think, okay, well, if all of these strings, that's a language for which I don't have a DFA, for example. Well, certainly if I have a bigger, like a language with more strings in it, it has to not be language. No, sorry, that can't be regular either, right? And unfortunately, that's not actually the most careful of reasoning, actually, because it could be the case that when you have a less specific language, that it could be the case that that is indeed regular. So let me give you a counterexample to this claim here. So that's why I'm saying the answer is no. So let's consider this. So suppose L2 is equal to sigma star. Over some alphabet sigma. So you can think of it just as 0 and 1, and then you have actually all binary strings. That's what sigma star would be in that case, if we had zeros and ones. So that would be all binary strings. Now the question, is the set of all binary strings, is that regular or not regular? Well, let's see. Let's see. So this is actually another way of me asking the following question. Is there a regular expression that describes all binary strings? And the answer is yes, there is. It looks like this. Equivalently, you could define a DFA that's going to have a small number of states, maybe 1 or 2, that most certainly is capable of recognizing sigma star over there. So that means that this language over there, sigma star, that is most certainly regular, right? I could give it to you as a regular expression. I could describe it with a DFA, right? But notice that this is actually the superset of all languages, right? This is so like if I give you like all binary strings and then I look at any subset of those, that would be, for example, like if I considered this one over here, the one with equal numbers of zeros and ones. This is indeed a subset of this one, right? Do you see how the relationship actually doesn't hold? It has much more to do with how to specify the strings, not if they're a proper subset or not. So when it comes to claims like this, you have to be careful. So if you have a very simple to describe set of strings like this one, it could be the case that it is regular. But we're going to see that all sorts of different languages have all sorts of different properties. And even ones that are subsets of sigma star could be even, they may be not regular, right? They may also be even harder to recognize than just simply being not regular, which we'll explore in the future. So, that being said, this concludes our example, and I hope you found this interesting. So just be careful. If somebody tells you, they ask you, is sigma star regular? The answer is yes, it is. And that is, in fact, a superset of any, like if I consider sigma or alphabet being 0 and 1, that is, in fact, the superset of any one language, right? Over the binary symbols. So if somebody asks you this question, the answer is no to this more broadly, right? In general terms, the answer is no. So are there any questions about that? Is that interesting? So this should feel a little counterintuitive at first if you're familiar with how complexity, like how you think about complexity of problems. Because remember, we can think of these languages as decision problems. So this should be a little bit strange because you think, okay, well, if they're in this language, then that means that they must be, there's like a hardness that comes with that. But the thing is, at certain levels, it depends. It depends. So when you think of nicely like categorizing these like this, some of them are going to be within the set of regular languages. Some might not be. And the membership of those strings, like which strings they belong to, that may have nothing to do with if it's regular or not. Because indeed, all of them are in sigma star, even though sigma star is in fact a regular language. By the way, I thought that was an interesting thing to wrap things up on, and also gives you an interesting thing to be careful about, is that indeed, if I give you some superset of a non-regular language, it may be the case that it is indeed, yes, that it is also not regular, as in this example over here. In fact, the way I used and proved this claim, I used the fact that that is in fact the subset of it. However, the general statement of it is, it's not true. It's not true, because I can easily give you examples like this one, where L2 is, in fact, sigma star, which is a superset of any one of any language you're interested in. But yeah, no. Are there any questions? Any questions at all? But just as a reminder, the notes for this will be available afterwards. So they'll be later today. I'll put out an announcement over the social media. And also you'll get a notification over on Patreon when the notes are available over there. So I'm not seeing any questions. So if there aren't any questions, I want to say thank you so much for coming on by. Make sure you tell your friends to come join the fun here, where we learn more about computer science. Keep in mind that on Thursday, I'll be back live again. I'll be playing some more Chrono Trigger. We just went back to the ancient times. We're heading into the Raptite layer. And of course, consider subscribing, supporting, following. Tell your friends, of course, as I already told you. And consider letting us know what you think. There's that survey
Thank you
that's
for
in the
another great
description.
lesson.
And hopefully you found this interesting. I know that this will be one of the last few things I'll talk about with regular languages. I might talk about next week, I might be talking about properties that regular languages have when it comes to testing them. So for example, if I wanted to know if two languages that are regular are equal to each other, I might talk about that next week. If not, I'll talk about minimizing DFAs. That might be one possibility. If not, I might talk about something else. We'll see. In my schedule, I have it testing properties of regular languages. So if all fails, we're going to talk about that. So, no, you're welcome. You're welcome. So anyways, I'll let everybody go for your day. I want to say thank you for coming on by and have yourself a beautiful day. I'll see you later.